So again, welcome to our lecture. That is the flexible AC transmission system. Today, we are going to discuss the improvement of transient stability. The basic and the review of transient stability has been taken in the last lecture, where it is found that the transient stability is evaluated with the help of equal area criteria. The equal area criteria is nothing but the acceleration and deceleration should be equal to 0. Whenever there is a large disturbance, after large disturbance, the machine or the synchronous alternator is going to oscillate, and this oscillation should be die out very quickly. So the transient stability is going to judge by the equal area criteria. Now, the objective is that to evaluate or examine the transient stability with the help of FACT devices. What is the effect of FACT devices on the transient stability? Can we improve the transient stability with the help of FACT devices? Or presently we are discussing the shunt compensation. So effect of shunt compensation over the transient stability. So for that purpose, we will take the two machine system. Earlier, so this is earlier, we have considered two machine system. The machine is connected with the transmission line. Without compensation, without shunt compensation. So this is the two machines. Voltage E1 and E2 and reactance is X. If E1 is equal to E2, say this is voltage V, we can write the equation of power P is equal to E1 E2 upon X into sine delta. Or simply the power P is equal to V square upon X into sine delta. This is the two machine system without any shunt compensation or ideal midpoint compensation. Whereas again, the two machine system, same two machine system, it is connected with the shunt compensation, ideal shunt midpoint compensation. So this is the reactance. As we are connecting the midpoint shunt compensation, the total transmission reactance, it is divided into the two part. So it is E1 as it is, this is E2, and here is the shunt compensation, ideal shunt compensation. So it is injecting the current at the point of connection. So this is the reactance is X by 2, this reactance is X by 2, and by doing some vector diagram and all these things, directly just I will write here the power P is equal to twice V square upon X into sine delta. Delta by. So what is the difference? The difference is that in these two equations, suppose this can be written as P maximum into sine delta, where P maximum is equal to V square upon X. So similarly, this equation is nothing but it is the twice P maximum into sine delta by. This is the equation. This is uncompensated line. This will write it is a uncompensated, and this is midpoint shunt compensation. So this is the difference between these two one. Now we'll see the power angle characteristic in both cases. So this is the P delta curve. The power become maximum. Here the power become maximum at pi by 2. So P maximum, because this is the power P on y-axis. On x-axis, this is the angle delta. So it is going to occur maximum at pi by 2. This is 0 and this is pi. And for a compensated line, shunt compensated line, the power angle characteristic is this is power P, this is angle delta, and which is the uncompensated line. Just we will draw the first is an uncompensated line. And from that uncompensated line, with the reference of uncompensated line, we are going to draw the compensated power. So it is a P maximum, and it is going to occur at pi by 2, isn't it? Now, for the compensated line, it is P is equal to twice maximum at sine delta by 2. Means when delta is equal to 180 degree or it is equal to pi, then the power going to become maximum. So here the power is going to become maximum, and we can say that for the compensated line, the curve would be like that. This is the compensated line, and the equation of this one is P is equal to twice V square upon X into sine delta by 2. Okay, and here it is an uncompensated one. So it is simply, it is P is equal to V square upon X into sine delta. Okay. Now, our topic is to examine the transient stability. Our topic is to examine the improvement of transient stability, by shunt compensation. Now, in this case, uncompensated line, the system is operating at this point, that is the point over here, where the mechanical input is equal to the electrical output. This topic has been covered in the last lecture. So whenever the fault occurs in the transmission line or in the somewhere in the two machine system, somewhere the fault is occur, so the power goes to the output power of the generator goes to the 0, whereas the mechanical input remain constant, and hence generator will accelerate. So the generator will accelerate. Under such condition, d delta upon dt is greater than 0, and generator is going to accelerate. It will accelerate till the opening of the circuit breaker or clearing of the fault, and because of this one, it will say it will develop the acceleration curve or area under acceleration. So this is acceleration area A1, whereas to make the acceleration area is equal to deceleration area, that is the say condition for the transient stability, and say up to this one it is going to make equal is the deceleration area. This is area A2. How to calculate the area A1 and A2, which we have already covered in the last lecture. So area A1 become equal to area A2, the system will be stable, isn't it? So transient, it is because of the sudden and large disturbance. Any application of the fault, sudden increase in load, there may be some tripping of the generator, one of the big generator in the system. The transient conditions comes, and most of the fault are the transient in nature, or especially on the transmission line. So this part, which is shown by this red area, this one, it is the margin for the transient stability. This is the margin, area under margin means, it means that this much is the marginal area to maintain the transient stability. For example, the same system, suppose the generator is going, the circuit breaker is going to open over here in this point. This is that point. So under such condition, this total area is going to utilize to make it equal to the acceleration area. So here we can say that this is the clearing angle, delta C. This is the initial angle, operating angle, where the system is operating before perturbation, delta 0. And this is the maximum angle at which the system may remain in the synchronism, and that is called as a critical clearing angle. Now, what would be the change if we are connecting ideal shunt compensation in the transmission line? Now, say for example, same mechanical input, same condition is there. This is the same condition over this one, where the mechanical input and electrical output is same. System is operating under equilibrium condition, and this is the operating angle, delta 0. This is delta 0. Now suppose the fault occur, and same up to this same, it is going to open the circuit breaker at this point. So this will be the area under acceleration and deceleration. So say this is the, here, this is acceleration area. When the output of the generator becomes 0, input of the mechanical input will remain same. And since the mechanical input remains same, the generator is going to accelerate. And this is the deceleration area. This is A2. Now see, here, this is the marginal area. This is the margin for the transient stability, whereas with the help of shunt fact controller or shunt compensation, this is the area available. This is the area available. I will give this is the area. Very large area is available under ideal shunt compensation. So we can say that there is an improvement in the transient stability. This is the area of margin. So see, this is the small area. So there is a large chances the system may come out from the synchronism or unstable, the transmission line. Whereas this is the additional area available, or large area is available. So in this case, we can say that the transient stability can be improved with the help of shunt compensation. Now, initially we are operating. Initially we are operating at this point. So power transmitted will be this one. This point is equal to, say, at any this angle is P is equal to V square upon X into sine delta 0, isn't it? Now, in the compensated line, it is possible to operate our system somewhat higher angle, and hence the power transmitted may be, it is definitely greater than the earlier case, say delta 1. So this point is P is equal to twice V square upon X into sine delta 0 2 divided by 2. Okay, so this is the case, and here, even though the circuit breaker is going to open over here, but we will have large area to make balance between acceleration and deceleration. So we can say that the critical clearing angle delta CR for the compensated line is greater than the critical clearing angle with uncompensated line. So all these points conclude that the transient stability improve the shunt compensation, ideal shunt compensation improve the transient stability of two machine system. So this is the points of this is one. Now we will take a second point in the today's lecture. It is a very short one. So this point is power oscillation and damping. Power oscillations and was for oscillation damping. So whenever there is a perturbation, any type of perturbation, especially for the transient condition, followed by the perturbation, the generator is going to oscillate, is an angular oscillation. So say there is initially the system is operating at some particular angle. This is time t, and it is operating at delta 0, similar to this delta 0. Suppose there is a sudden increase in load, so it will take some oscillations, and after few oscillation, it is settled to the new equilibrium position or new angle delta 1. So the study of 1.5 cycle is the transient stability study, and whereas how it is tracking to its new equilibrium position, that brief period, is the dynamic stability. But if the system is undamped, there is a continuous oscillation in the power system. So it is occur because of the unbalance between mechanical input and electrical output. How it is? It is can be explained by this 3 diagram, and how the shunt compensation is going to mitigate the oscillation. Say, for the undamped, the angle is going continuously damping. There is some oscillations in the angle. Okay, so this is the undamped system. Undamped. This is the time t, and this is the delta or delta 0. Say this is one figure. Now, because of this one, how it is going to occur? When delta d delta upon dt is greater than 0, it means that the mechanical input is greater than electrical output. Electrical output means simply it is because of the mechanical input slightly greater than the electrical output. and the system is going to give the acceleration area, means the acceleration, and there is a continuous damping is there. Because of this oscillation in the alternator, the power also get oscillate, and this oscillation may lead a severe problems. So there's a tie line oscillations and all these things. It is going to occur because of this one. So power also get oscillate. Power get also oscillate, and so on. So it is the undamped power. So it is the power P, and it is the time T. So again, it is a undamped. Now, if we go do some shunt compensation, and shunt compensation is synchronized in such a way that it will increase and decrease the VAR output. Definitely, this oscillations may be die out or mitigates with a very effective manner. So it is the reactive power QP, and it is we are going to inject in such a way that, so during this one, the reactive power is get injected, and here the reactive power is deficit, and so on. So because of this reactive power provided by shunt compensation, the oscillation mitigates. So this is the oscillation is going to mitigate, and this is the damped system. It is the damped one. Similarly, the power also damping in the power curve also mitigates, and finally it is going to settle very quickly. So we can say that the shunt compensation has three main some advantages. The point number one, which we have already, which I have discussed, that first point, it increase the power handling transmission ability of the two machine system. And earlier, for the uncompensated line, the power P is equal to V square upon X into sine delta, just we have done. And whereas with the help of shunt compensation, ideal midpoint shunt compensation, the power handling capability of the transmission line would be, theoretically it is would be twice V square upon X into sine delta by 2. Just we have drawn this curve. So it is double to the previous condition. Second, it maintained the voltage profile. This is for the two machine system, no doubt. This is for the two machine system, and whereas for the radial system, means the there is a source, transmission line, and it is load. So load compensation, this is called as a load compensation, because the shunt compensation, shunt compensator, we are installing at the near to the load. So this is the compensator which we are installing, and because of this say compensator, end line compensator, it is found that the voltage profile of the radial transmission line is maintained very effectively. This is the curve already covered. So there is a flat voltage, or the voltage profile is very nice under such condition. So this is the voltage V, and this is P. Say for example, this is for the 0.8 lag power factor. This is unity power factor, and it may be 0.97 leading power factor. So this is the second advantage of shunt compensation. And the third advantage, just we have covered, it is the improvement in transient stability. So transient stability is improved with the help of shunt compensation. The improve in the transient stability is nothing but the very well can be understood with the help of these two figures is that the marginal area is going to enhance with the help of shunt compensation. So this is the third. And fourth point is the point it will die out the oscillation in angular motion, as well as because of this one there is a power oscillation in the transmission line and tie out or say power oscillation in tie line. It can be mitigated with the help of shunt compensation. So at the end of this shunt compensation, the summary of the shunt compensation or the requirement of the shunt compensation is that the point number one, the compensator must stay in synchronous operation with AC system at the compensated bus under all operating conditions. So whatever the shunt compensator we are installing, either it may be the midpoint or either it may be the end of the load or say load compensation, it is very much necessary that this is the shunt compensation. It should be synchronized with the AC bus where it is connected under all operating condition. All operating condition means during the normal as well as the fault condition. If it is not supporting during the fault condition, definitely it has no meaning. Okay, so in all condition it should be synchronized. Second is that a component must be able to regulate the bus voltage for voltage support and improvement in the transient stability during because of this some application of the fault, and somewhere any fault followed by there is a change in the voltage and all these things. So under such condition, it should maintain the voltage and improve the transient stability as well as the voltage stability with the help of end voltage support. And because of the end voltage, the system may come out from this one, or you can say that the voltage collapse. So it should avoid the voltage collapse and improve the transient stability. And for the next one, for the transmission line connected to two machine system, the best location of the shunt compensator is the midpoint. For the two machine system, this is two machine system, the best location of the shunt compensator is the mid of the transmission line. Okay, so it is also there. We can install some more shunt compensator along the transmission line. Say the transmission line, it is divided into the fourth part. So again, this is two machine system. So the midpoint, the best location of the ideal shunt compensator is the midpoint. So we can install here the shunt compensator at the midpoint. Now for this section, this is the midpoint. Again, we can install the shunt compensator at the midpoint and so on. So this is also explained in the book under book for the understanding facts by the Hingorani. This is the shunt compensation, which will improve the transient stability, power handling capacity, and so on. And for the radial line, this is for the radial line, the best location of the shunt compensator is near to the load. So it is a load compensation. So this is the, say, highlights up to the shunt compensation. Now, next time, next lecture, we will take the method to control VAR generation by a different combination. It may be a thyristor control reactor, thyristor switch reactor, and thyristor switch capacitor. Thank you.